Okay, so let's talk about hypothesis testing for means. Okay, so in our first example, we're going to talk about the annual household income. Okay, so in 2003, the Census Bureau found that the annual average income for a household in the United States, annual average income is $68,728. Okay, so that's in 2003. So a researcher nowadays is interested in knowing if that is still a good, if that is still the average income, right? So a researcher goes out and they researcher randomly samples. They go out and they randomly sample 49 people, okay? Randomly samples 49 people, people in the United States who have an income, and finds that their average income is $72,542. Okay. The standard deviation Okay, so the standard deviation is $15,200. All right. So the researcher wants to know if the average income in the United States has increased, right? Why increase? Because of inflation. Makes sense. So they want to know if it's increased. They want to use a significance level of alpha is usually how we notate our significance level, and I'll talk more about what it means. But they want to use a significance level of 5% or 0.05. Okay, so that's another piece of important information. All right, so they want to test if the average income is increased. Now you could, before you've taken a statistics class, you could say, oh well, 72,000 is more than 68,000, right? So it's increased, right? Done. Drop the mic, walk away, right? But now that you've taken a statistics class, you know that that's not the way it works, right? That was an estimate from these 49 people. Don't forget, there's a population out there, right, with a true population mean. Now, a population mean, we'll use the mu notation to represent it, okay? So there's a true population mean out there, and what we've done is we've gotten a sample, and we've estimated x bar, the sample mean, right? But we could have gotten a different sample, and there would be a different sample mean, right? This number is random. A different sample would have a different sample mean. So the question is this 72,000 significantly more than 68,000? Or is it just due to random variability that you see in it is more? Make sense? Okay? So let's go through how to do that. And that's what the whole hypothesis testing is all about, is trying to determine if something is significantly different than another thing, significantly more, significantly less than another number, than the population number or the previous number, right? So that's what hypothesis testing is all about. So the first step to any hypothesis test, step 1, is to state your hypothesis. Okay, and in statistics, we have notation, right? And same notation always. We have this HO and HA. HO stands for the null hypothesis, all right? And the null hypothesis is always going to be, in a case where you're testing a mean, right? What we're testing is a population mean, okay? And it's always going to have the equal sign. And it's always going to refer back to whatever the population mean was in your example. In this case, we're testing, is this sample mean more than this number here, right? So this is our population mean. Okay? And the alternative hypothesis is whatever you're testing. So in this case, we're testing, is the true population mean more than 68,728? Make sense? So we're testing, is the true population mean more than what it used to be, right? So that's step 1. Step 2 is always calculate your test statistic. Okay? So right now, our test statistic for population mean, there's a formula on our formula sheet, right? So you have this formula sheet on your exams. Under chapter 8, right, there is 2 different test statistics when you're doing a hypothesis test for a mean. Okay, the first one says sigma known, and the other one says sigma unknown. Okay, now in this case, sigma. Now remember sigma. What is sigma? Sigma is a population standard deviation, right? So maybe I should write that up here. So sigma is the population standard deviation, right? We learned that a long time ago. And S, right, is the sample standard deviation. Which do I have?
The sample standard deviation.
Why? Why do you say that? That's true. Why?
Because you have the standard deviation of the 49 people, not of the Census Bureau.
Very good. So this is the standard deviation of my 49 people, right? So it's a standard deviation of the sample. So I have a sample standard deviation. Okay? But you know what I'm about to tell you? That we should be using the test statistic for sigma known. Okay? Now why is that? Well, it turns out that if your sample size is large enough, in this case, what's our sample size?
49.
Okay, so N is 49. If your sample size is large enough, then you can assume the sample standard deviation is a close enough estimate to the population standard deviation that you can just go ahead and use the sigma known situation. Okay?
So what's large enough?
So what's large enough? For this class, we'll use a cutoff of 30. Okay? So
arbitrary.
Yeah, it does seem that way, but actually 30 is a pretty good estimate as long as your original data is not skewed too badly, right? So
it doesn't matter if your original population, like what if you're studying something rare and your original population is like 10, then, and you take a sample of 3 people. I don't know.
Okay,
you know what I'm saying?
so the population size is, in statistics, it's never going to be just 10 people, right? So say you're studying like a rare disease.
Uh-huh.
Okay, and you wanted to know what would be the average, what you'd want to know.
Mortality, how long they live. Or something.
Okay, so the average lifespan of people with this rare disease. Okay, so in that case, the population would really be the true average lifespan of someone with that disease. That for someone with that disease that's ever lived or ever will live. Right?
Okay.
So even in a rare disease, you still have a true population standard deviation, and in that sense, it's the whole ever lived, ever will live, the true population average lifespan. Okay? So when you have a sample and it's only 10 people, then you don't have large enough, and you cannot make this assumption that the sample's standard deviation is close enough to the population standard deviation. Only 10 people is not enough. Okay?
Okay.
Make sense?
Okay.
So in this case, my sample size is 49. It's considered to be large enough that we're allowed to use the sigma known situation. Population standard deviation known. Okay, so if you go to your formula sheet, the test statistic that you should use when sigma is known is z equals x bar minus mu over sigma over square root of n. Okay? So now all I have to do is plug in these values and solve for the test statistic. So let's talk about what each of these values are. Okay. So what is x bar?
That's the sample average?
Mhm.
So 72, 342.
Oh, that's a 5.
Oops.
5, 4, 2. Okay.
Minus
Okay, mu.
68, 728.
Yeah, good. So that is mu, right? You always calculate your test statistic assuming the null is true. That's why the null always has the equal sign. Okay? So your test statistic is always calculated assuming HO is true. And that's a general. Okay? So that's why mu equals 68,728. Make sense?
Sure.
Okay. Sigma, right, which we're going to assume, right, that is close to the population. Okay, and then n is 49. Okay, so let's go ahead and plug all those things in. Okay, plug it into your calculator. If you're watching this video, I recommend that you plug this into your calculator right now. Practice plugging this into your calculator. Make sure that you have your numerator in parentheses, right? And then you have a divided sign, and then your denominator also in parentheses. So make sure that you can calculate this. When you calculate it, you should get 2.64. Okay, so I've run out of space, so I'm going to go ahead and erase and make some of this neater. Okay, so we've calculated our test statistic, 2.64. Okay, so that's step 2. Step 3 is going to be p-value or critical value. Right? Right now, I'm going to talk about p-values. Alright? I will come back and redo this. We'll pause the video, we'll make a new video, we'll talk about critical values, okay? So you can solve this problem using either method. Most of the time on exams and such, we'll be using p-values. P-values are what people use mostly nowadays. But when you're doing your homework in my stat lab, sometimes they'll ask for critical values. So that's why it's important for you to know how to do that. And then later, we'll do a type of test that only we'll be able to do using critical values. So it's important for you to know how to do both. Okay. All right, so talking about p-values. So p-value. All right, so p-value, what is that, first off? That is the probability that you would observe a sample mean that is this extreme, assuming the null is true. Okay? So if the true population average income is 68,728, what's the probability that you would observe an average income of 49 people, 72,542? You understand?
Mm-hmm.
So what's the probability that you would observe that if the null is true? So p-value, you always assume null is true, right? Assume HO is true. Okay? Now.
So hang on a second. So the smaller the sample size, then the more likely you're going to have an extreme value. So then your
by just chance.
By chance, so then your p-value goes up. Right? Because your probability of observing that increases.
Potentially, right? So remember, your test statistic also would be different because remember on the denominator you saw the square root of n there.
Mm-hmm.
So that is going to have an effect on your z-value. It'll make your z-value smaller, the smaller your sample size is. So, yeah.
Okay.
Hmm?
So yes, the p-value will go up. Not directly, you're saying.
Yeah, I'm saying, okay, so let's say I had this exact same sample mean, but only 36 people. Then yeah, the p-value would be higher. Yeah,
Gotcha.
That's what you're asking. Yeah. Okay. Okay. So small p-values, right, mean that it's unlikely we would have observed this sample mean if the null was true, right? Large p-values will mean that it's likely we would observe this given the null is true.
Mm-hmm.
Okay. Okay. So you're assuming the null is true. Now I just drew a distribution. What is that a distribution of? Well, remember I said sample means are average, or sample means are random, right? This 72,000, it's a random number, right? Mm-hmm. So there's a distribution for it. So this is the distribution of the sample mean of x bar, right? And if the null is true, then in the center of that, right?
68, 72.
Yeah, is this 68, 72, okay? And so our observed value was up here at 72,542, okay? So what is a p-value? It's a probability of observing a sample mean that's this extreme or more extreme. Okay, so I need to basically figure out what's this area. That's basically what I'm trying to do, right? So, what we're going to do is basically change this, instead of it being a distribution of x bar, let me change this to the distribution of z, of our test statistic value. Okay? Now, remember the formula for our test statistic. Let me write it down here. X bar minus mu sigma over square root of n. What's in the center here for the distribution of z? Right? What is, if this is x bar is 68,728?
You're saying the distribution of your test statistic.
Mm-hmm.
So what is the average
so remember,
test
the
statistic?
test statistic is also random, right? Because it involves this x bar, right? Everything else is not random, but this x bar is random, right?
Uh-huh.
So if sample mean is random, then so is z, right?
Okay. So
what's in the center? So if the sample mean were 68,728, then what's the value of z?
Why isn't it 0?
It's 0, right?
Oh, okay.
Yeah. In the center it's 0, right? Because if you plug in 68,722 into x bar, then you get that mu minus mu, basically, so 0. Right?
Mm.
So, I mean, basically, what is this calculation? It's a transformation from the distribution of x bar to the distribution of the sample statistic, right? So this corresponding number here, it corresponds to something number on here. Well, what number? Well, 2.64, right? Make sense?
Oh, interesting.
Yeah?
Okay.
Does that make sense?
Sure.
Okay. So that's what the p-value is. It's this area here. Now, why did I do that transformation? Why did I do that? Well, because we don't have a table that has, like, I have this table here, and in the center of that table is 0, right? I don't have a table that says 68,728 in the center of it, right? So if I want to find this area I've shaded in, I got to use this table. And the only one way I can use this is if I do this transformation. Does that make sense?
Mm-hmm.
Okay, so that's what's going on here. So the p-value, either way, it's this area here, and those areas are exactly the same. This is just basically a transformation from one distribution to the next. Does that make sense?
Yeah.
Okay. Okay. So I want to find this area here, okay? So this is the distribution, assuming the null is true. Let me write that down here. assuming HO is true. Okay, so now at this point I want to find the probability that Z is greater than 2.64. That is what that's what my p-value is going to be. Okay? Now, remember this table only gives the area behind a certain Z-value, right? So in order to find that forward probability, I'm going to have to do 1 minus, right? The total area is 1. So if I say 1 minus the probability that Z is less than 2.64, right? Basically 1 minus that back area. So look at my table for 2.64. 0.9959.
Wait, on your second line, probability Z, you flip the sign? Is it greater? We went from greater than to less than?
Yeah, because greater
Okay.
than means this, right? Less than is this.
So you're doing the whole.
So I'm doing
gotcha.
1 minus this.
The less than.
Yeah. Does that make sense?
Gotcha.
So 1 minus this, and then that leaves me with what's back here. Alright, so if you do that, then you get 0.0041.
Does that table have, what does that table have on it?
Yeah.
It just has a...
So you look up the Z value. So it tells you for particular Z values. So
So for
you look up the
2.6
first 2 digits here. So 2.6, and then you look up the third digit here. So 2.64. 2.6. Yeah, 4.9958. Yeah.
Okay, so that gives you the number of the back end.
Yeah, it gives you
Okay.
the shaded area.
So it didn't matter the notation of less than, greater than. Because the table always gives you
the less than. Yeah.
Okay, gotcha.
Yeah. The
Okay.
table. So we want to find this greater than.
Yeah.
So the table will give us the back
Always
end.
give you the
Yeah.
back end, okay.
Yeah. Does that make sense?
Yep.
Okay. So that is our p-value there. Okay. So I'm gonna go ahead and erase that. So let me write this again. .64. This area, the p-value equals 0.0041. Alright. So that's doing p-values, right? Like I said, we'll come back and we'll explain this process again using critical values in a minute. Okay, so now last step, fourth step. Actually, I guess some people break the fourth step into 2 different steps, so I'll do that. Okay, so I'll do 4 and 5. So the fourth step is to go ahead and say either reject the null hypothesis or fail to reject the null hypothesis. Okay, so those are your 2 options, really. You have to say just like that. Reject HO, okay, or fail to reject HO at significance level, and you should specify your significance level. So at significance level, now that's where I said alpha equals 0.05, we'll be using that later. That's the significance level. So reject HO at significance level 0.05. So you have a choice. Either reject the null hypothesis at significance level 0.05 or fail to reject the null hypothesis at significance level 0.05. Okay? So we found this p-value, right? And that's a really small number, right? So if we're assuming the null is true, this area, the probability of observing that this test statistic, the probability of observing this sample statistics, what I meant to say. So the probability of observing this sample average is really low if we assume the null is true, right? 0.0041. Right? And really, really low, what I'm saying is less than 0.05. That's what the significance level, that's how you use the significance level. Make sense? Okay, so it's really, really low. So that means, what do you think? Are we going, so this is the null hypothesis, are we going to reject it?
Yep.
Yeah, we're going to reject it. We're going to say, no, this is not reasonable, right? The probability of observing a sample mean of 72,542, if the true population mean is 68,728, was really unlikely, right? So we are going to reject the null hypothesis. Okay?
So we found that the probability of getting, the probability of seeing an average income that high is 0.4%, right?
0.4%.
Yeah,
okay.
0.4%. So it's very unlikely, less than a 5% chance that we're going to see an income that high if the mean is 68. Therefore, the true mean must be greater than 68,000 in order for us to witness something that high.
That's right. So that's the second part of writing our conclusion. So you always write your conclusion first with regards to the null, and then you said, and therefore, the true population means more, right? So, and therefore, we have to say something with regards to our alternative hypothesis, okay? So, we reject the null hypothesis, and then we say, there is evidence, right? So there's evidence to suggest that the average income for households is more than 68,728. Okay, so you're saying something about the alternative now. Okay, now this second part, you always write this in a way that a layman can understand, right? Step 4 is always written like this. You have 2 options, and they're both something only a statistician would understand. But your last sentence should be something that anyone can understand, right? So that's your conclusion. Okay? All right. Any questions about that?
No, I don't think so.
All right, so let's go ahead and talk about critical values next.